This is the 13th installment of Advanced J1939. I have the picoscope connected to a CAN bus which has, we'll take a look here, we'll zoom out on it. We have two controllers which are on this bus. So I have a transmission controller and I have an engine controller. And we can see, we'll take a look at this source address. This is the source address is 03, so this would be the transmission controller. The transmission controller, whatever type of transmission, if it's an automated manual or it's an automatic, this controller, source address 3, is transmitting a message. We'll take a look at this one from the engine controller. This is the engine speed message. We can see that it's source address 0. We can see that the message is, because there's only two controllers, the transmission controller is acknowledging that this message has been received correctly. We can tell that by the acknowledge bit. We can see that this is all occurring error-free. If I were to zoom out, we'll take a look at the transmission message. So this is a message by the transmission controller, and it appears that the engine controller is acknowledging that it's seeing this message correctly. We can see that the amplitude of this acknowledge bit is just a little bit higher than the logic 0 bits, which are being transmitted by the dominant bits, which are being transmitted by the transmission controller. This is typical. Even though there's only one controller that's acknowledging, the amplitude's just slightly different because it's a different controller. It's got it's located somewhere on the bus, a ways from the engine controller, and the electronics in it are not exactly the same as those in the engine controller. So we have a little variation in the amplitude of the acknowledge bit, even though it's just the one controller which is acknowledging. Okay, let's go ahead and zoom out, and I'll start the scope over again. And we can see that by the traffic, by the loading of this bus, it's not heavily loaded. I don't know, maybe 20% loaded, just looking at it, eyeballing it, if even that. But what I'm going to do now is I'm going to disconnect the transmission controller from the CAN bus. And what you're going to see will be this. And what's occurring is now I only have the engine controller on the CAN bus, and I'm going to guess that this CAN bus is nearly 100% loaded, and it's only one controller that's there doing it. Let's take a look at one of these messages and let's see what's wrong. We can see that this is PGN EF FF, which is being transmitted by the engine controller, source address 0 with a priority of 3. So it's a pretty high priority message. We can see that the data is all present. We can see that the CRC is being sent out. What we're missing is there's no one out on the CAN bus to acknowledge that this message has been received. So the engine controller will then retransmit that same message. You can look and see that it's the same data. It's the same PGN, everything is the same, but still nobody's acknowledging. Because of this, the engine controller is going to keep trying to transmit that message repeatedly. So if I were to look at this on an oscilloscope and see something like this, there may not be a problem. The problem may be that there's no other controller on the CAN bus by design. So let's say that it's just an engine or it's some other component which is connected on J1939, happens to have a diagnostic connector. You connect up to it and you see this. This is just indicating that there's no one there on the bus to be able to acknowledge me. If you tried to connect a service tool to this, let's say we're going to diagnose the engine. If this were an engine, some industrial application, engine by itself driving a pump or something, I would not see this. I would not expect to see this then, because my service tool, whatever it is, the electronic service tool, the adapter, the device which connects onto the CAN bus, onto the 9-pin diagnostic connector, would provide the acknowledge bit. Otherwise, it has to act as a controller that's on the bus. Otherwise, that diagnostic tool would not be able to do anything because the CAN bus is pretty much fully utilized. So this is one of the tricky things, or some of the tricky things, I guess, with J1939. The way that this controller might respond, this engine controller might respond if no other controllers on the CAN bus, it may do just as this one is doing and continue to keep transmitting the messages over and over and over again endlessly. So if I looked at this a day later, it may be still doing this. some other engine controller, another manufacturer, or even the same manufacturer, but some other vintage, it may be designed so that if nobody is there listening and it gets so long, let's say a few seconds, and nobody's responding, it stops transmitting. And in order to then be able to make a connection, a diagnostic connection in that kind of case, I might have to have the service tool connected from the very beginning. So at an initial key cycle, it would come on, it would see it, and it would allow it to then, that controller to then communicate. So this is one of the tricky things if you're trying to diagnose CAN where there's no other controllers on the bus. Why would you diagnose CAN if there's no other controllers on the bus? Well, as I said, if you have your service tool and I'm trying to connect the service tool to reprogram the controller or to diagnose a problem with that system, be it an engine or whatever it is, I need the service tool to be able to connect. So it becomes my other device that's on the CAN bus and would provide the acknowledge bit. Okay, I've loaded a waveform which I captured on a machine where I was able to actually detect some errors and was able to capture that information and to save it. So taking a look at this, we can see that there's activity that's on the CAN bus. We've got a few controllers that are on the bus. Let's take a look and let's zoom into this one message in particular here. So we're going to take a look at this message. I can see that this is from the engine controller. This is our PGN. This is basically a request for information. This PGN EFFF, it's requesting all controllers for some information. I'm not sure what it is. The reason why I can't be sure is because this message has been corrupted by some controller. If we take a look at the data, we can see that everything starts out and looks normal. We can see that we're reading in, this is our length of the data, so it's going to be 8 bytes in length. We can see as that data starts being transmitted, some of the controller has taken over the bus or has decided that I don't like something about this message, or this is a defective device. This is a device that isn't, it either has a problem or it's detecting, or it itself has detected a problem with the CAN message. So any controller that's on the bus, it doesn't matter whether that controller cares whether or not any messages that come from, for example, the engine controller, if it detects a problem, one of many problems, and these problems could be due to physical issues with the bus, so shorts and opens, intermittent shorts and opens. What that any controller can do is basically interrupt the controller which is transmitting the message and cause it to detect that it's being interrupted and to then have to try to retransmit that message. So how does it interrupt it? We talked about the stuff bit and this violation where you can't have more than 5 bits in any one direction at a time. During a message. So let's take a look. We can see that we have, looking at this, it looks like, what's our delta time? So we have 4 microseconds. So this is 2 bits. That's our 500K. This is being whatever the device is, whichever controller. It looks like it's the engine controller is transmitting this message. Some other controller, and we don't know who it is, even though this has dropped down, we can see that the time, this delta time, is 407 nanoseconds. That is billionths of a second. So these billionths of a second, 400 of them, is a really short period of time that the CAN bus has. This is not going to be counted as a logic 1. So what we're detecting as far as picos detected as far as an error is, we can see from this time to the end of this time, 12 microseconds, that would be 6 dominant bits in a row. So if we don't count this because it's too short in time to be seen as a recessive bit, we would see, or the pico or other components, other devices have detected, there is a bit stuffing violation. And this could actually be some problem with that controller, with another controller, or some intermittent power supply connection to it. I've seen things like that where a controller may come onto the CAN bus and not really follow the rules very well and come onto the bus and just start communicating immediately. Not something they're supposed to do, but it happens. So what happens because of this violation, we can see a couple of things. So let's take a look here. We can see there's a little ripple here. There's a whole lot of information that's here. This is about, here's 6 bits, so this is about 12 microseconds. The controller has seen some error. Whatever controller it is has seen an error, and we don't have any way, there's no information that tells us who this is, right? There's no source address or anything associated with it, so it could be anybody that's on the CAN bus has detected that there's a problem, and um, and so it will broadcast intentionally 6 dominant bits in a row. In this case, from 500K, that's 12 microseconds. That is a signal. That's a flag to every controller on the bus and to the controller which is transmitting that there's been an error detected. So this period of time is some controller detecting that there has been an error, and it's intentionally put 6 bits in a row. Whenever the other controllers have also detected the bit violation at some point, they detected it a while back, they also started transmitting their 6 bits in a row. So somewhere back here in this period of time, this may be a little difficult to understand, so somewhere back here they detected, right here at this point, that a bit stuffing violation. So the other controllers, even though the original one, the one that detected the error first, the other controllers also are going to signal that they see that. So they also have that same 6 bits in a row. You may see this lag. So in all, we end up with errors being signaled for something close to 20 microseconds. So that's 10 bits in a row that we put a dominant bit out there. That's probably more detail than you'd need to know, but it may help you explain or to understand why, when we have errors detected, why isn't the same length of time? Why don't I see this flag for an error being the same duration and time? Part of it is because that's when the other controllers, all the controllers, if there's multiple ones, have detected the error. They may not detect it at the same time as the original, I'll say, complaining controller, so whoever that was. So what happens because of this? We can see that that message, that EF, we can see the same data, the same start of the data is being retransmitted by the engine controller. It has to be retransmitted. There's a pause, there's a period of time here where there's nothing being transmitted. And so now it must retransmit the whole message. And this second time, everything went through okay. And the other controller, at least one controller on the CAN bus, provided an acknowledge bit. So we'll go into next time a little more detail and maybe some other examples of how errors are flagged on the CAN bus.